today in this session we will learn about the motion of satellites round the earth in circular orbits. So, you see, let us first see the orbital velocity, how much velocity the satellite should be there, should be given so that it orbits our earth. So, this is our earth. So, first of all we will satellite which we will learn here should be in circular orbit. In next session we will see different orbits. So, first here the orbit is circular. So, let us first calculate orbital velocity of a satellite round the earth in circular orbit. So, let us see how to calculate that. Now, you see this satellite has a mass m and the mass of m earth is capital M. Now, let us assume that this distance is small r and the radius of the earth will be, I have reserved the capital R to be the radius of the earth. So, when the body moves in circular path, the necessary centripetal force is given by the gravitation. The gravitational force provides the necessary centripetal force for the satellite to move in the circular path. So, let us see its dynamics. So, the force F due to gravity gives m times v square by r. So, this is v orbital. So, v orbital will be written as VO. Now, this force is g mass of earth into m by this r square is m v naught square by r. So, this m cancels, 1 r gets cancelled, implies v naught is under root g m by this r. So, this is the orbital velocity. Now, if this r is, now if r is nearly equal to r, i.e. the satellite is close to the earth surface, then we have v naught is equal to under root gm by r, which can be written as gm by this r by r square, that can be further written as root over, this is acceleration due to gravity g into r. This value is nearly 8 kilometer per second. So, the expression for orbital velocity is root over gm by r. If it is close to earth, it is root over gr. Now, let us study the energy of a satellite in its circular orbit. So, this is earth and at a distance r we have a circular orbit. So, let us first calculate kinetic energy. So, the kinetic energy is given as half mv square, which is, already we have seen that this v naught orbital velocity is v naught is equal to root over g m by r. So, it will be g m by r. So, we will write this k as g m m by 2r as equation number 1. This is the kinetic energy possessed by the satellite when it is in the circular orbit. Now, potential energy is P. So, this U will be the potential energy of this satellite M of mass M when orbiting round the earth M will be given by G M by R. So, you see here this U is actually, this is equation number 2. Now, total energy will of the satellite, that will be denoted by E, that will be K plus U. This K is G by 2R minus G by R, that becomes minus G by 2R. So, we have the energy expression as minus G by 2R, that is the energy of the satellite in the orbit R of radius R. This is the expression for E. So, let us summarize the expressions. K we got as, you see, K is modulus of E, we can say, that is equal to G by 2R. U is equal to minus G by R, and total energy is the negative minus G by 2R. So, you see this, all the three expressions are very important. So, here just as a footnote I am writing, that I will discuss later on. The energy is negative means the system is bounded. The negative energy of E shows that the system is bounded. So, now let us see the time period of the satellite. Now, this time period T is given as 2 pi r by orbital velocity. Now, this 2 pi r by orbital velocity expression, recall, it is given by G by R. So, this is root over Gm will be here by R. So, this is time period. So, we have T is equal to 2 pi by root over Gm, and this R plus R to the, that is R by 3 by 2. So, this relation again if I square it is written as 4 pi R square Gm by R cube. So, implies time period square is proportional to R cube, which is, we will see later on, that of famous Kepler's relation, Kepler's law. So, thus you see the time period is 2 pi root over Gm by R to the power 3 by 2. Now, let us see a special type of satellite called geostationary satellite. Now, in this satellite, the time period of this satellite matches with the time period of rotation of earth. So, you see this is the equatorial plane and the earth rotates about its axis. This is axis of rotation of earth. Now, when a satellite is such that it moves along the equatorial plane, so it moves in the equatorial plane, so that its time period matches with that of the earth. So, you see earth rotate, it also rotates with the same time period. So, what happens if you see the satellite is here, then this is a point fixed to the earth. So, this satellite is directly above earth, this is the center of earth, and so it is directly above it. So, now what happens when this earth rotates to this position, the satellite also rotates to this position. So, this is P1 position, now it is P2, this is S1 position, so it rotates to S2 position. So, in this case the satellite appears to be stationary with respect to Earth, that is any observer will find that this satellite is not moving. So, we will call it geostationary satellite. Its another name is that geosynchronous satellite. So, when the time period of this satellite gets synchronized with the time period of Earth, then this satellite is called geostationary satellite. So, when the time period of a satellite gets synchronized with the time period of rotation of Earth, then the satellite is called geosynchronous satellite. At this condition, the satellite appears to be stationary to the observers on Earth. So, we call it geostationary satellite. So, its two names are there, geosynchronous because its time period gets synchronized with the time period of rotation of Earth, and since it appears to be stationary with respect to any observer on Earth, so its second name geostationary satellite. So, now let us calculate what is the height of the geostationary satellite from the surface of Earth. So, let us evaluate the height of the geostationary satellite from surface of Earth. Let us evaluate this. So, in order to evaluate, what we will equate the time period of the satellite. So, already we have seen that the time period is given as 2 pi r by v, that is equal to 2 pi r by root over gm will be here and root over r, that is 2 pi r to the power 3 by 2 by root gm. Now, if this is equal to time period of the rotation of Earth, that is Earth rotates one complete round in 24 hours, that is 86400 seconds. So, if I put this value and then we will solve it, we get this implies r we will get nearly 4.2 into 10 to the power 3 kilometer. So, this is the distance of the geostationary satellite from the center of. So, the distance of this satellite, geostationary satellite from the center of Earth is 4.2 into 10 to the power 3 kilometer, that is 42,000 kilometer. So, the height from the surface of Earth becomes r minus radius of Earth, that is 42,000 kilometer minus 66,400 kilometer. So, this will be nearly 36,000 kilometer. So, this satellite is 36,000 kilometer, that is nearly 6 times, you can say 5 to 6 times more than the radius of Earth above the surface of Earth. So, when a satellite is at this height, then it will appear to be stationary to any observer on the earth. So, now let us see escape velocity. So, you see, if this is the earth and if we are here and if we want to project something vertically upwards, so if velocity is more and more, so it will go more and more distance above it. A stage will come when the ball will never come back. That velocity will be called escape velocity. That means it is the minimum velocity, it is the minimum velocity, it is the minimum velocity, that must be given to a body at the surface of earth, so that it never returns back. So, what happens? So, if it never returns back means it goes to infinity. So, at infinity the energy of any object is 0. So, its potential energy is 0, and since I have to give the minimum velocity, that means it just manages to go to the infinity. So, what we have to do in order to calculate the minimum velocity, we have to equate the energy on the surface of earth S to the energy at infinity. So, equating the energy at the surface of earth of the mass to the energy of the mass at infinity. So, when energy on the surface and energy at infinity. So, energy on the surface is, we are giving this kinetic energy and it has also got the potential energy due to the earth, and this is the kinetic energy at infinity and potential energy is 0. Since I have to give minimum energy, so this energy should be also 0. That means I have to give this gets cancels. So, V is equal to 2 gm by r root. We can further write it as 2 gm r by r square. This is acceleration due to gravity on the surface of earth, that is 2 gr. This value comes out to be 11 point something 2 kilometer per second, something 11.2 kilometer per second. So, this is the escape velocity. So, when we throw a ball, suppose I throw a ball from here. So, you see here I have thrown vertically above. You see, even if I throw it at some angle alpha, then also the velocity escape required. So, whatever the angle of projection may be, if I throw anything, if I give this speed to anything from the surface of earth, then it will never return back. This is what escape velocity is. Now, come to motion of a double star system. Here we will learn about the concept of reduced mass. Now, often we have found that in universe there are two stars which orbit round each other. So, what happens actually, there we have this as the center of mass. So, this star orbits and this star orbits, they orbit around their common center of mass. So, center of mass. So, let us find what is the energy, momentum and time period of such a double star. Now suppose this is m1 and m2 mass and this total distance is r. So we will have r1 and r2 as this distance, center of mass. So from mechanics you see r1 will be this m2 times total distance, m2 times r by m1 plus m2, and this r2, this side r2 is m1 times r by m1 plus m2. This is how r1 and r2 is from the center of mass. So from the dynamical equilibrium of m1, we have on this m1 force G m1 m2 by r square, that is equal to m1 omega square r1. So let us substitute m1 r1 from here. So we get G m2 by r square as omega square r1 is m2 r by m1 plus m2. So further omega we want to calculate, this m2 again gets cancelled here. So we have G m1 plus m2 by r cube is equal to omega square. So omega is actually, omega is equal to this. So omega is equal to G m1 m2 by r cube. So we have thus we now calculate time period. So time period of the double star T is equal to 2 pi by omega, that is 2 pi by r cube by G m1 plus m2. So this is the expression for the time period of the double star system. So now let us calculate the angular momentum and the energy of this double star system. Angular momentum of the system. So you see here L is equal to, now two masses are there. So I1 omega plus I2 omega. Omega is same. I1 means m1 r1 square plus m2 r2 square into omega. Now m1 is here, m1, recall r1 is m2 r by m1 plus m2. So this is square plus m2, r2 means m1 r by m1 plus m2 whole square, and this is omega. So we can take something common, that will be m2 square. So I will take m1 m2 r square by m1 plus m2 whole square common. From here we will get m2 and here I will get m2, and from here I will get m1. So this will be get cancelled, and omega, let us replace omega by root over G m1 plus m2. So this one gets cancelled. So you got m1 m2 r square by m1 plus n2 omega. This is written as mu omega, where mu is called reduced mass. So where mu is called reduced mass. So mu is equal to m1 m2 by m1 plus m2. So you see here, this is the angular momentum. If I assume that mu is something moment of inertia of a single mass, then you just imagine that we can imagine a two body system as a single body system with mu as the moment of inertia. So mu is something which replaces these two mass system. So, this is called reduced mass. So, whenever you have a two body system here, that term can be replaced mu omega r square is also there. So, mu is called here the reduced mass. Now, let us calculate the kinetic energy in the system, in this double star system. K is half I1 omega square and for another body half I2. So, we have half I1 plus I2 omega square. So, you see again I1 is mr square, that is this term. So, I1 plus I2 already we have calculated, and you see this term is I1 plus I2 mr square. So, this is again this much. So, this finally we got I1 plus I2 as this term. So, we will get m1 m2 by m1 plus m2 r square, this is I1 plus I2 omega square. So, this half is also there. So, this can be written as mu. So, implies K is equal to half this mu, this half mu r square omega square, r square omega square. So, you see this mu is the term which are using for m1 m2 by m1 plus m2. This is m1 plus m2, this is called reduced mass. So, this is the expression for the kinetic energy.